Hi students. In this second video for online lecture 8, we are now going to talk about the naming of ionic compounds. As you can see by the title slide, this means that we're going to bring in the dreaded polyatomic anions. So let's talk about the nomenclature as a whole. For ionic compounds, it is often going to be a metal and a nonmetal. The anion, the nonmetal, we are just going to add the IDE ending to the elemental name. You are going to see the common elemental anions located here at the bottom. That is how we go from fluorine to fluoride, chlorine to chloride, bromine to bromide, and iodine goes to iodide. So notice that we can now get our species BaCl2. What we are going to do is take the elemental name of our metal and leave it the same. So that is why we get barium, but now we need to go and change our chlorine to chloride. If we have this species, K2O, notice that we have potassium, and then finally we have to go and look for the anion of oxygen, and if we see it here with our group 6A, that is going to be oxide. This is potassium oxide. So then finally, we go to this species. Notice that I have Mg, and now we have the species that is OH something. This is what we call a polyatomic anion. I will show you the list that you are expected to know. This is a group of atoms that has a charge and likes to form ionic compounds. So what we need to do is know our metal name, which in this case is going to be magnesium, but then you also need to know your polyatomic anions to know that this is going to be hydroxide. So the successful name of this is going to be magnesium hydroxide. So it's really important that you not only know the elemental names for our metals and our anions, which you see here, but you also need to know the polyatomics because we are going to see them over and over throughout the remainder of this course. So now we get a new species. So a lot of people are going to look at this and say, well, it contains potassium, nitrogen, and oxygen, so it must be potassium nitrogen oxide. No, the problem is that our potassium is going to be our metal, but NO3 is another one of our polyatomics. In this case, this is known as potassium nitrate. There are going to be some polyatomics that are just the difference of one oxygen, and that is going to change the spelling of our polyatomic. So we must be very careful. So let's look at the common monoatomic ions first on the periodic table. A monoatomic ion only contains one atom. You see them here for sodium plus, chloride minus, calcium 2 plus, oxide 2 minus. It's anything that is elemental and only has one atom. Here on the periodic table, you are seeing the common ones that we have. Notice that the transition metals can adopt different charges. We're going to have to look at the context clues to see those differences. You are expected to know the charges of all the representative elements. That means that you must know your alkali metals and your alkaline earth metals, going from the aluminum group all the way over here to fluorine. And then there are three transition metals that only adopt one charge. Those are zinc, cadmium, and silver. Those only adopt one charge. When it comes to something like our tin 2 plus and 4 plus, or lead 2 plus or 4 plus, or any of the transition metals, we are going to have to look at the context clues as to what it's bound to in order to figure out its charge. The other thing that we have to worry about is the polyatomics. These contain more than one atom. They are grouped together covalently, but they have an overall charge that likes to bind ionically to a metal. Groups of that are OH minus, that's going to be hydroxide. We get to Cn minus, which is typically cyanide. The only positively charged one that we will deal with as a ion for salts is ammonium, NH4 plus. And then finally, we can see that here is our NO3 minus that we saw in the previous slide. This is going to be nitrate. So which ones are you expected to know? I have grouped these here of all of not only the monoatomic atoms that have a singular charge, but also the polyatomic ions in here as well. You can also look at the front slide of this lecture to see a much larger group of the anionic ones. I would expect you to know many of these as you're going through. An important part in all of this is that you'll see that some of these compounds have two names. Let us go ahead and look at chromium-3 or chromic. The chromic name is old school. We historically do not use those. If I look at cobalt-2, it is actually named cobaltus, which is one of my favorite words in all of general chemistry. But what we are going to do is choose to use the Roman numeral nomenclature that I will show you here in a moment. So if it has multiple charges as a metal atom forming the ion, we are going to use the Roman numeral notation. As you can see on the right side, not only do I put in my halogens, but I'm also going to put in many of my polyatomic ions that you are expected to know. So we looked at the transition metals. Now we must go and use what is commonly called the type 2 Roman numeral numbers. This needs to indicate the charge on the metal so that you know which one you are dealing with. So let's go ahead and look at this species. We know it contains iron. It also contains chloride. So many of you are going to look at it and say, Dr. Collins, that's iron chloride. Well, the problem with that is that we need to signify that this iron is actually 2+, because there are multiple versions of iron. So it is best for us to label it as iron, parentheses, the Roman numeral 2, then chloride. The reason because is now I also have this species, which is iron chloride. But now you can see because I have 3 chlorides, which are each 1-, that means that my iron must be 3+. I will signify that by calling it iron 3 chloride. So when you are not sure as to the charge on our metal, you must signify it with a Roman numeral. That means you will never do this with the alkali metals, the alkali earth metals, or your zinc, cadmium, and silver because they only have one charge. However, if we're using any of the other transition metals and we use the likes of tin or lead, you must signify what the charge is on the metal based off of using a Roman numeral. Now you can see here that I have chromium and sulfide. Well, what's the charge on my sulfide? That's going to be 2-. So I have 3 of them. That gives me a total positive charge of +6. So now what that means is that I must take that 6+ divided by 2. So this is chromium 3+. This means that I need to name this as chromium 3 sulfide. It's really important that you know the difference of when to use the Roman numerals and when not to use the Roman numerals. So let's go ahead and look at this compounds that we see here. So first off, notice that I have cobalt. Cobalt can adopt many charges, and then I must know my polyatomic that we see right here. Do you remember which one that is? Well, this is going to be nitrate. It is fully expected by your exam time that you know that nitrate is NO3 with a 1- charge. The reason that this is important is that if our nitrates individually have a -1, and there are 2 of them, we have a -2 charge that we must balance. This means that our cobalt must be +2. So this means that I have to go and name it with that. So the correct name for this would be cobalt. Now I need to go in and put the Roman numeral, so I will put this in as cobalt 2, and then I need to name the polyatomic anion, and that is going to be nitrate. The correct name for this is cobalt 2 nitrate. Let's go ahead and drop down to our example C here, and notice that I have a unique cation in this case. This is the polyatomic cation of ammonium. So this is going to start as ammonium. So now for my ammonium, this is going to have a +1 charge. And now I have a -1 charge on my ClO3 species. Which one is this going to be? Well, you could look it up on your chart and you're going to end up seeing that that is chlorate. This is ammonium chlorate. There is going to be a series of compounds that can be very difficult. Notice that you could get ClO1 minus, you could get ClO2 1 minus. We just saw it in this example here of ClO3 1 minus, and then finally ClO4 1 minus. This is typically what we call the chlorate series, but each one of them has a different name. They all have the same charge, and you have to be incredibly careful that you know which one is going to be which. The best way of learning this is using flashcards and working through these any chance that you can get. So let's look at this final example. Write the chemical formula for the following examples. I have mercury 1 nitrite. Now, mercury 1 is a little bit of a fickle beast. The reason why is that it actually comes as a diatomic. This is one that you'd have to know as Mg2 2+. So this means that each one of them carries a +1 charge, but they like to be together. So now I have to ask you, what is nitrite? Well, that is going to be NO2 1 minus. This differs from nitrate by 1 oxygen. So now I have to look at the charge balance. How is this going to balance very easily for us? Well, if I do this, I would end up getting Hg2, and yet I will need 2 of these NO2s to balance the charge, and you will see that that would be my correct chemical formula. Let us go ahead and look at our cesium oxide. Well, cesium is really nice because it is an alkali metal and it's always going to be +1. Our oxide is always going to be -2. So what is going to be my chemical formula? Well, I need 2 cesiums in this case, so I will get CS2 and I will get my 1 oxygen, and it is CS2O. So finally, let's look at example C with our magnesium phosphate. Our magnesium is a alkaline earth metal, so that is Mg2+. And now we need our phosphate. Phosphate is going to be PO4 3-. So now our best rule for this is using the least common multiple, and that is going to a charge of 6. So what I would like to do in this case is go to Mg and use 3 of them. That way I can get to +6. And then finally, for my phosphate, it is going to go to PO4 and getting 2 of them. Notice you only use the parentheses when you are using multiples of the polyatomics. I do not use parentheses for the 3 with the magnesium, or in the second example, the 2 with the cesium. But if you are going and using multiples of the polyatomics, you need to put those in parentheses. Be very careful with that notation. In this last example, now let's go ahead and try this. If you are wanting to create an ionic compound with cadmium metal and phosphate polyatomic ion, what would that formula look like? So now we need to go back and remember the charges on those species. So we have cadmium. That is going to be Cd. But remember, this is a transition metal that has only 1 charge. In this case, it is going to be 2+. So what is our phosphate? Well, that is going to be PO4 3-. So this is the least common multiple rule again. So that way you want to go to Cd. I need 3 of those. And then finally, I would need PO4 2 in order to charge balance. And if I do that, you will see our answer D. In this video, you saw the importance of ionic nomenclature, not only when to use Roman numerals and when not to, memorizing the polyatomic anions, and also when you are supposed to use parentheses or not, especially in the case of our polyatomic anions. This is a skill that I expect you to know and work on continuously as we go through many of our word problems, because I may give you chemical compounds in a written form, and you are going to have to write balanced chemical equations using the chemical formula that you create. In the next video, you're going to see how important our covalent nomenclature is and how drastically different it is going to be. That is going to be for our next lecture. In the meantime, have a great day.